You missed the joke.
That was funny.
Stand up. That's true.
Okay, you guys are doing okay? Today will be the last day of algebra review. So I am going to, last time we talked about polynomials, today we'll talk about the rational functions. But before that, let me give you a couple of graphs that you need to know, because I'm going to use them as examples later. So some of the root functions, some of the basic root functions. So you should know the graph of the following. Oops. Okay, so the graph of root x, right? So what's the graph of the function y equals to root x? Well, we know that it's basically something like this. And so that's the graph of root x. Again, y is equal to root x. That would mean that y squared is equal to x. And we know that the graph of y squared is equal to x is a parabola opening to the right. So there is another part to the parabola, right? The green part is the graph of what? What function? Negative root x. Very good. And the blue one is the graph of the root x function. Now, if I ask you what is the graph of x to the 1/4, so notice that this is x to the half, right? What's the graph of x to the 1/4? So in red, I want to draw the graph of x to the 1/4. Okay. So what would be the graph of that? Well, remember the graph of x squared, x to the 4, x to the 6, the even powers of x. We drew them, right? The graph of x squared and x to the 4. We also drew the graphs of x cubed, x to the 5, x to the 7. We know how they look like. Similar things happen here as well. So let's say here is 1, okay? Right here is 1. So this height here is 1 as well. When x is bigger than 1, which function is bigger? X to the 1/4 or x to the half? So what I'm saying is that when x is larger than 1, okay, or equal to 1, which function is bigger, x to the 1/4 or x to the half? Well, we can, let's take x to be 16, right? What is x to the half? 16 to the half. What is 16 to the 1/4? Which one is bigger? What was that? This is bigger, right? So we know that after this point, the graph of x to the 4 would be below the graph of... They have the same shape, okay? It's just like x squared and x to the 4. They have the same shape, but x to the 1/4 is going to be below x to the half when x is larger than 1. What is happening to the between 0 and 1? So after 1, it's got to be below, right? After 1, it's got to be below. What's happening after between 0 and 1? Which x to the 1/4 is bigger, right? For example, think about 1 over 16, right? 1 over 16, what is 1 over 16 to the power half? 1/4. 1 over 16 to the power 1/4 is 1/2, right? So which one is bigger? X to the 1/4 is bigger. So that means between 0 and 1, the red one would be in fact above the blue one, right? So the red one is the graph of the 4th root of x. Can someone tell me the graph of 6th root of x? Between 0 and 1, it will be above what? Above the red one, right? And after 1, it will be below the red one, the 6th root of x. Same way for 8th root of x and so on. Now, for you, as an exercise, what you want to do is you want to look at the graphs of x to the 1/3, x to the 1/5, x to the 1/7, and so on. I'm going to show you what's the graph of x to the 1/3 here. So now we look at what's the graph of x to the 1/3. So if I am looking at the graph of x to the 1/3, right? So if I raise both sides to the exponent 3, I get y cubed equals to x. So remember the graph of y is equal to x cubed, right? We know the graph of y equals to x cubed, right? And now we are asking for the graph of x equals to y cubed, right? So if you view x as a function of y, the graph would be the same shape, except that it's going to be extending horizontally, right? The same shape. So the graph would look like what? This is the positive x-axis, positive y-axis, and so the graph looks like here like this, and then like this, right? This is like you flipped the graph of x cubed, right? It's the same shape, except that it's it's extending horizontally to both sides, and so that's the graph of x to the 1/3. Okay, what would be the graph of x to the 1/5? We'll have the same shape, except where will they differ? They will differ at between -1 and 1, and then outside of -1 and 1 they will be different, right? Which one would be above and below? To the right of 1, x to the 1/5 will be below, right? Between 0 and 1, x to the 1/5 would be above, right? And so on for the other. So as an exercise you should do that. I'm not going to do it. One thing I want you to realize is that, remember the graph of x cubed, right? What is the slope of the tangent at 0? When you look at the graph of x cubed, what is the slope of the tangent at 0? The slope of the tangent at 0 for the x cubed function is 0, right? Now what is the tangent here at 0? The tangent is actually vertical. Okay, so it's a vertical line. Y-axis is a tangent to the curve. And I'm going to talk about tangents more later. But for now, at 0, the tangent line is vertical, which is the same as the y-axis. Is everybody okay with that? Okay. There is one more graph that I want to show you, which I want you to remember, since I'm going to use that later, is the following. The graph of x to the 2/3. It turns out that the graph of x to the 2/3 looks like this. Okay. And this is the y equals to x to the 2/3. X to the 2/3 is the same as x to the 1/3 squared, right? So that's why the graph lies above the x-axis, because it's always non-negative. And this is how the graph looks like. Okay. All right. And I just want to point out one more thing here, which is if I take a point, for example, here, right, and look at the tangent line at that point, and if I look at the tangent line at that point, let's call that point P. Then as P approaches 0, so as you move P towards 0, those tangent lines at P will become vertical. As you move toward the origin, the tangent line, the red tangent line, will become vertical. Is that making sense? Okay. Okay. Those are some things that you want to remember later. I'm going to come back to these examples and use them for some other purpose. Okay. So now, what is a rational function? Rational function let P and Q be polynomials with Q is not the zero polynomial, okay? A function of the form P of x divided by Q of x is called a rational function. So what is a rational function? Well, it's just a ratio of what? It's a ratio of two polynomials, right? Okay, anyone remembers the definition of a proper rational function versus improper rational function? What is a proper rational function? So P of x divided by Q of x, this fraction or rational function is proper. Well, for just rational numbers, right? What is a proper fraction? What is an improper fraction? Anyone remembers? 2/3, is that proper or improper fraction? Proper. And 4/3? Improper. So proper rational function simply means that the degree of the numerator is what? Is smaller than the degree of the denominator. So that's what we mean by proper. And then this is the same thing is improper. Improper if the degree of P is larger or equal to the degree of Q. Okay. So can someone give me an example of a proper rational function? So yeah, so if I have, which is 1 over x, so if I have, say, x plus 1 over x cubed plus 3x minus 1, that's proper. How about x over x minus 1? Improper. Or how about x squared plus 2x plus 1 over x to the 4 plus 2? That's improper as well, right? Okay, again, it just means the degree in the numerator larger than the degree of the denominator is improper. Degree in the numerator smaller than the degree in the denominator is proper. Okay. Any questions on that? Yeah.
Why is the last one proper? It's higher than the other.
Because I made a mistake. Not that I was checking you, but okay, let's just keep it that, and then it's improper. All right. So there are a couple of rational functions for which I'm going to give you their graphs, just because I'm going to use them to explain certain ideas later. So what's the graph of 1 over x? Does anyone remember that? What's the graph of 1 over x? So this is the origin right here. What would be the graph of 1 over x? The graph of, so we are looking at y equals to 1 over x. Notice that when x is big, the fraction 1 over x is what? Is small, right? When x is big, 1 over x is small. So if you increase the denominator, the fraction gets smaller and smaller, right? It gets closer and closer to 0. And on the other hand, when x is close to 0, right? When x is close to 0 and positive, then what can you say about the fraction? Well, then the fraction is big. For example, if x is 0.01, what is 1 over x? Okay, 100. When x is 0.001, what is 1 over x? So you can see that the closer x is to 0, the bigger 1 over x is, right? So what happens when x is close to 0? When x approaches 0 from the right, the function blows up, okay? So it becomes big. So that means the graph, near 0, the function blows up. And then as x goes to infinity, the function decreases, right? The function will never become 0, but it gets closer and closer to 0. And what happens when x is negative? Well, same thing happens, except that now the function has negative values, right? So now when x is negative, the graph looks like this. Is everybody okay? Is that making sense? So that's the graph of 1 over x. Now, if I ask you what is the graph of, let's say, 1 over x plus 2, what would you say? How would you obtain that? Yeah, so let me make a separate graph for that, in fact. It will be just easy for me to do it. Okay, so if this is still 0, and I have to shift it 2 units to the left, as you said, because it's x plus 2. So what you have to remember is that how are you obtaining 1 over x plus 2 from 1 over x? You are replacing x by x plus 2. And when you do that, then it's a shift to the left by 2 units. If it is 1 over x minus 2, it's a shift by 2 units to the right. And so in this case, let's make another vertical line at negative 2. So let's say negative 2 is right here. So here I have negative 2, let's say. So then the graph is just a shift to the left by 2 units, so it looks like this. And here it looks like this. Is that making sense? What happened? What happened is okay, so okay, so that's the graph of y equals to 1 over x plus 2. Okay, here's another example. This will be different from the other ones. So let's say I have the function, the rational function, which is x squared minus 4 divided by x minus 2. What would be the graph of that? Well, what you need to realize is that this rational function x squared minus 4 over x minus 2, notice that if I replace x by 2, what do I get? I get the numerator would become 0 and the denominator would become 0. So I get something like 0 divided by 0. So because when you replace x by 2, you get 0 over 0, it means that 2 is a root of the polynomial in the numerator, 2 is the root of the polynomial in the denominator. Which means x minus 2 is a factor, is a common factor of the numerator and the denominator. So because x minus 2 is a common factor, you should be able to cancel that out. So you can factor out this one as x minus 2 times x plus 2 divided by x minus 2, and then you can cancel out the x minus 2s and you get x plus 2. However, this equation holds as long as what? X does not equal to 2, because when x is 2, the fraction is undefined. When x is 2, this guy is 4, right? So what is this telling us? This is telling us that both functions are equal except at 2. Both functions are equal except at 2. So their graphs are the same. Their graphs are the same except at 2, right? So what do I get? I am going to get, what is the graph of the line y equals to x plus 2? The line y equals to x plus 2, well, when x is 0, you get 2. So let's say this is 0 and this is 2 here. When x is negative 1, y equals to x plus 2. When x is negative 2, you get 0, so you get a point right here, let's say. And so that's the line. This is negative 2 and this is 2. Okay, so this is the graph of y equals to x plus 2. And let's say this is 2 here and this is 4. The graph of the fraction would be then what? The graph of the fraction would be the same line, except that at 2 it has a hole, right? Is everybody okay? So I guess let me use a different color here, green. So this is the graph of x squared minus 4 over x minus 2. Same as the graph of x plus 2, except there is a hole at 2. Okay, so we are done with review. One more example. Okay, let's go over one more example. Suppose that I have y equals to absolute value of x minus 1, right? What's the graph of that? Well, we have to know, basically, first of all, the graph of absolute value of x. And since we know it, let's use that. So how am I obtaining this function from absolute value of x? And I'm replacing x by x minus 1, right? So the graph of absolute value of x we know is this one. It's a V-shaped graph. So what would be the graph of this one? Well, so this is the y equals to absolute value of x. And the graph of this one would be a shift on toward what? To the right by 1 unit, right? So this guy will go to this point here, let's say. And so what I get is this and this. So this one here, that's the absolute value of x minus 1. Okay. How about then the graph of absolute value of x squared minus 1? Do I obtain this function from x squared by replacing x by x minus 1? No. If I look at the function if I look at the function absolute value of x squared, that's in fact the same as x squared, right? Because x squared is positive. And I do not obtain the function that I started with so if I replace x by x minus 1, what do I get? I get x minus 1 squared, right? Which is not the same as what I have. So this is not a shift. This is not a shift of x squared graph, right? So how do I graph that? Well, let's do the following. Let's make our x's first. So whenever you have an absolute value function, draw the graph without the absolute value first. So what is the graph of the function without the absolute value? Without the absolute value, what's the graph? Anyone? It's a parabola starting at -1, right? The vertex would be at -1. And here's -1 and 1 as the x-intercepts. So that's the graph of x squared minus 1 without the absolute value. Now think about what's happening then. When x is bigger than 1, the value of x squared minus 1 is already positive. So when you put absolute value, it doesn't change, right? So the graph of the absolute value function would be the same as the graph of x squared minus 1 when x is bigger than 1. Same thing happens when x is less than -1. When x is less than -1, x squared minus 1 is already positive. When you put the absolute value, nothing changes. So the graph stays the same. What is going to be different is when x is between -1 and 1, right? When x is between -1 and 1, x squared minus 1 is negative. So you have to make it positive, right? So it's just the opposite of that, right? So you're basically going to flip the graph along the x-axis. So the graph would be this, and this, and this. So this red one is the graph of the function. Is that making sense? So whenever you have absolute value function, draw the graph without the absolute value, and then whatever the negative parts are of the graph, flip them. Flip the negative parts of the graph. Is that making sense? Okay. Okay, so a couple of more graphs that I want to show you. my x-axis. So this is where I'm trying to review some of these shifts, okay? That'll be the last thing that I do. Okay, once again, let's say I have the graph of x squared. So when x is 1, the value is 1. When x is 2, the value is 4. So 1, 2, 3, 4 right here. And then I'm going to get a point right here at -1, and I'm going to get a point right here, right? So this is the graph of y equals to x squared, right? So this height here is 4, and this height here is 1. Okay, my question to you is, what's the graph of 2x squared? So how am I obtaining the 2x squared? I'm just multiplying the function by 2, which means that the height of the graph at each point will be doubled, right? The height of the graph at each point will be doubled, which means it's a vertical stretch. Okay, so the point at 1 will go where? At 2, this point here. The point at 2, so this is 1, this is 2. The point at 2 will go to 8. Let me see if I have room for 8. 1, 2, 3, 4, 1, 2, 3, 4, way up here. Okay, so the graph of 2x squared would be like this. And of course there will be another part which is like this. So it's a vertical stretch of the graph of x squared by a factor of 2. What if instead of 2 I multiply by half? It will be a compression by a factor of 2, right? In that case the height, so let's draw that. In that case the height at 2 would be what? 2. The height at 1 would be half right here, half right here, 2 right here. So the graph would be a compression. So this would be the compression of x squared by a factor of 2. Is everybody okay with that? All right. So that's 1. Okay. One more. Here I want to compare the graph of f of x and graph of f of 2x. So suppose that you know the graph of f of x looks like the following. Whatever f is, I'm just giving you an arbitrary graph here. So let's say the graph of f looks like here. So let's say this is the graph of some function f, and the domain of that function is from 0 to 2. Okay, we are just sketching the graph from 0 to 2. So this is the graph of f of x, and I'm not telling you what f is. That's the graph. What would be the graph of f of 2x? That's what I want to ask. So notice that here I am not multiplying the y value by 2, right? I'm not multiplying the y value by 2. I am multiplying the input value by 2, right? So what's happening? Well, remember the domain here for f is what? X is between 0 and 2, right? So f of 2x, right? F of 2x will be defined. F of x will be defined as long as 2x is where? Yeah, it has to be between 0 and 2 because that's the domain of f. So then x would be where? Between 0 and 1. So the domain of f of 2x is between 0 and 1. Okay? So what's going on here is that when you multiply the input value by 2 to obtain a new function, it's not going to be a stretch, it will be a compression along the x-axis. It's a horizontal compression. On the other hand, it's sort of like the opposite of what happened when you multiplied x squared by 2 and half. Instead of having f of 2x, if I have f of half of x, what's going to happen is that it's going to be a stretch. So let's draw this f of 2x. Well, the point at 2 will go where? The point. So this is 1 here, okay? So the point at 2 will come right here. Let's make some changes. So let's say this is half here. This is here 3.5. Okay. So the point at 3/2 will go where? 3/4, right? 3/4 is where? Right here. So the point at 3/2 will come here, and the point at this is where 1 is, will come to half, right? The point at half will go where? 1/4, and the point at 0 will stay at 0. So the graph looks like this, okay? Well, drawing, I guess you get the idea. So the graph of f of 2x is this. But if I look at the graph of half x, then it will be a stretch, right? Then the graph will extend from 0 to what? 0 to 4. Okay? Same shape, but compress or stretch. Okay? All right, this is it. This is the end of algebra review. And I'm happy we are done with this. Since I don't have too much time today left, I am going to review a little bit of trigonometry today instead of starting section 1.5. So section 1.5 is the start of calculus, sort of like something that you haven't seen in algebra. Okay, so what I want to review now is, first of all, some very basic stuff. So first of all, does anyone remember what is a line? Well, a line again is an array, and a line extends to infinity in both directions, right? So that's a line. Extends to infinity in both directions, okay? What is a ray? A ray means it's a half line. In other words, it extends to infinity in one direction. It has a tail. That's what I'm going to call a tail. This is a ray. Everybody's okay? What is an angle? 2 rays. Yeah, so if I have one ray and another ray having the same tail, right? Having the same tail, that's an angle. So this is an angle. Whenever you have an angle, one side of the angle is called what? It's called the initial side. Initial side. And I am going to denote that by I. And the other side is called the terminal side. Terminal side. And that's going to be denoted by T. The way you want to view this, though, is that you want to view that the initial side is always fixed. And then the terminal side always starts at the initial side. And then you revolve the terminal side either counterclockwise or clockwise in order to create your angles. Okay? So suppose that I have this initial side, and then I have this terminal side, so I and T. And let's say this angle is obtained by revolving the terminal side counterclockwise. Then this angle is a positive angle. Okay. Also, I can revolve the terminal side round and come back. Okay. I can make two complete revolutions and come back to the same point. It's a positive angle. Okay. What's the negative angle? Well, it's just the opposite of that. That is, you revolve the terminal side clockwise. So this is the initial side, this is the terminal side, and now you revolved clockwise. That's the negative angle. Is everybody okay? Now you might also be turning a couple of one complete revolution and then come back here. Still a negative angle. Again, negative simply means you revolved the terminal side clockwise. Positive means counterclockwise. Is everybody okay with that? What's the degree measure of angles? What is the degree measure of angles? So let's say this is the initial side, and you revolve the terminal side. You revolve the terminal side. One complete revolution. Then you come back to the initial side, right? So this is the terminal side, and this is the initial side, and that's the tail here. And then you made one complete revolution like this, okay? And we take that one complete revolution to be 360 degrees. Okay? 360 degrees means that. So what's going on here is that we divide one complete revolution into 360 segments. So imagine that you have the initial side here, and then you have 1 degree would be 1 degree is, let's say, looks like this. So that's like, say, 1 degree, and then I can make one more maybe. So my point is, one complete revolution is divided into 360 segments, and each segment represents 1 degree. Okay, so that's what we mean by the degree measure. So what is the measure of this angle then? What is the measure of this angle here? Well, that's just that's a 1/4 of one complete revolution, and that's what? Yeah, that's 1/4 of 360, and that's 90 degrees. What would be 180 degrees? Well, that's half of one complete revolution. So this is the tail, and that's 180 degrees, and so on. So you get the idea. Is everybody okay with that? The 360 degrees, why 360? Why not 1000? Why not some other numbers? Well, that's just historical reasons. The ancient Babylonians, the way we use 10 digits to represent numbers, 0, 1, 2 up to 9, because we have 10 fingers maybe, but they used to use 60 digits to represent numbers. And that's why so 60 times, so the number 60 came from there, and 60 times 60 is 360. 60 seconds, 60 minutes came from there. That's why we have that 360 degrees. And I'm not sure, did they have 60 fingers? I don't know, but well, I know they didn't. But okay, okay. So here is the what is the other measure? Radian measure. So let's look at the radian Radian measure. What's the definition of the radian measure? Well, for that I need a circle. So let's say I have a circle, and this is the center of the circle, and let's say I make a central angle at the center of the circle, and the angle is subtended by this arc here, and that arc here, and let's say that arc has length c, and the radius is r. Okay, so what's the radian measure of theta? What's the radian measure of theta? It's c divided by r. So the radian measure of theta is c divided by r. Okay, so it is a ratio of lengths, right? It is a ratio of lengths. That's the measure. Now, what's the conversion formula for the two measures? Well, okay, so what is the one complete revolution? In radian measure, one complete revolution is what? 2 pi, right? Because if you have one complete revolution, then what is the value of c? The value of c when the value of arc c, right? When theta is one complete revolution, then c is what? 2 pi r, right? That's the length of the circle. So you divide that by r, 2 pi r divided by r, that's 2 pi. So the radian measure of one complete revolution is 2 pi radians, right? So we also know that one complete revolution is 360 degrees, right? So that means 2 pi radians is what? 360 degrees. And then what is pi radians? 180 degrees. So so if I give you the degree measure of an angle, how would you convert that to radian measure? What do you multiply with? If I give you the degree measure, how do you convert to radian measure? You multiply by pi over 180. If I want to do the opposite, if I give you the radian measure, and if I ask you find the degree measure, then you would be multiplying by 180 over pi, right? You can remember that? Maybe let me write that down. To go from radian to degree, you multiply by 180 over pi. To go from degree to radians, you multiply by pi over 180. Is everybody okay with that? Is that okay? All right. I am going to review a little bit more about trig functions later. But I'm going to, you studied trigonometry for half a year, right? About half a year in high school. And I am going to try to give you everything about it in one lecture maybe next time. And so, yeah.
Do we have to memorize the unit diagram?
Yes, I'm going to tell you how to memorize that. Yeah.
Do we have a quiz in here on Friday?
I'm going to let you know tomorrow because I haven't looked at what I want to cover tomorrow and Friday. So at some point today, I'm going to think about what to do tomorrow and Friday. If I see that I need the class time, I might ask you to take it online. Otherwise, you should expect it in the class. 1.1, 1.2, and 1.3.